morning, konnichiwa. My name is Alfonso, and I'm going to present the recent work that we're doing at McGill University. And it's about the extraction of violin gestures from audio recordings. And when I say gestures, I mean sound controlling gestures, like bowing velocity, bowing force, etc. So we have like three different information domains: the score, the gestures, and the sound. About the same thing, the same musical performance. So there are techniques to map one of the domains to the others. So for example, if we have a musical score and we produce some sound, that's what we call sound synthesis. And if we analyze the sound and make a transcription of the score, that's what we call music information retrieval. But of course, those are the most important ones, but we can go from any of them to the others. So this paper is exactly there, so we're mapping sound to gestures. So we're going to analyze sound, and we're going to obtain how this recording was played. And we usually call it an indirect acquisition of gestures, because the direct acquisition would be to use sensors during the performances to measure the gestures. These are strategies that are very accurate. It depends which kind of sensors we're using, but in general they should be more accurate. But there are some problems that they may be intrusive and they're quite complex. And I would say that the main contribution is that of predicting continuous controls. Because in previous works, you can, for example, know the string being played in a note or the bowing technique of a note. But in general, those are things more related to the score domain, not to the gesture domain, the control domain. With that pickup. This has many advantages, like we have no body or room resonances. The audio acquisition is in the same location. That means if you have a microphone and you make several recordings, you don't know exactly where the microphone was, and even the performer is moving. So you avoid problems with that. But the models is restricted to that violin adapter. But I think it's like we have been using wide-corner infrared cameras, and we have been using electromagnetic field sensors by Volhibus, which are the ones in the figure. But the important thing is that we want to know at any moment the position of the strings and the position of the hair ribbon. So we're interested on tracking those red points. This is an example of the recording session where we can see that the family is playing and we're tracking them. And at the end, it is to have a database. This is representing the visualization of the database where we have the sound on the top. This is representing the score, the bows, the pitch, and the durations. And here below we have the gestures. We're going to extract features for the audio and features for the gestures. So regarding the audio features, we're comparing two sets. The first one, I call it low level, and it's basically the energy and frequency bands. And there is a second set, which I call perceptual, and it's like widely used descriptors used in audio analysis. And well, as you will see in the results, the low level, they work much better. We are estimating bow velocity, which is the derivative of the bow transversal position. We're computing bow reach distance. And we are computing this angle, which is called the grid. So the idea of at the end of the learning is to, for each frame of audio, we extract some spectral features, and with those spectral features, we want to be able to predict the gestures. Here we have what is inside the string prediction. So basically, you have the low level features, the bands and the pitch. Look like this. There is actually one perceptron for each prediction. So this is representing the prediction of the string. So we have the ground truth of the string, which is in red. In blue, green is the prediction, and you can see that sometimes there are like sudden changes in the prediction, which shouldn't happen because it's not possible if I'm playing. And this happens because we are not taking into account the time evolution. We're predicting frame by frame, isolated frames. So it's necessary to provide some stability. So there is a hysteresis function, it's basically a smoothing. And we can see after the hysteresis that many of the isolated peaks are gone. Correctly classified frames, and the rest is correlation coefficient. And so you can see two things. The low level features are performing much better, and then the prediction is like quite awesome. I'm impressed. It's possible to extract sequences of gestures from the sound, and actually quite accurate. The structured controls are related to if you remember the three domains, to the gesture domain.